Our study of sand transport in thin fluids is conducted in a slot 1 foot high by 8 foot long. There are 3 perforations at the top, middle, and bottom of the front. In this run, a half a pound per gallon 2040 sand is being added at 12 gallons per minute. There are 3 mechanisms for sand transport in thin fluids. The most efficient is traction carpet, shown here. When the equilibrium bed is formed, its height depends upon the flow rate and the amount of sand being added. In this case, we're looking at 12 gallons per minute with 6 pounds per minute of sand. The equilibrium bed height is about 26 centimeters of the total slot height, which is 30 centimeters. The traction carpet itself is approximately 1 centimeter wide. When sand is cut and the amount of sand entering the slot decreases, we begin to see erosion of the equilibrium bed, which maintains a significant amount of proppant in suspension for a significant period of time. As the velocity decreases, we begin to see the appearance of dune migration. While an inefficient means of sand transport, it still moves proppant toward the end of the fracture. At some point, the velocity gets low enough that we begin to see the third form of sand transport, and that is saltation flow. In saltation flow, individual sand grains are picked up and transported a small distance and then redeposited. This is a very inefficient form of proppant transport, but with continued flow results in a flat bed with a reduced equilibrium bed height. At a third of a barrel per minute flow rate and a half a pound per gallon sand, there is a large entrance effect due to the venturi flow through the perforations. Here we see all 3 sand transport mechanisms, from the traction carpet as the equilibrium bed height is developing, and at lower velocities, the dune migration and saltation flow. At a tenth of a barrel per minute per foot of height and a half a pound per gallon sand, the entrance disturbed by the perforations is much reduced. The angle of repose of the sand as it builds to the peak of the equilibrium bed height is clearly seen. When the flow rate was reduced by 1/2 and the sand concentration remained at a half a pound per gallon, the entrance effect is minimal. We see the sand building to the equilibrium bed height at the angle of repose, and the leading edge is also filling at the angle of repose. Alright, the lower perf completely sanded off. Coming in the middle, and upper perf.
And then have to go over the bottom of the floor. But he's supposed to mark them.
With a half a pound per gallon of 4060 sand in water at 12 gallons a minute, we see a slowly developing equilibrium bed, but viscous transport is more important, moving sand deep into the fracture. It takes much longer to equilibrate the bed height with 4060 sand, but after it had equilibrated, the bed height was 25 centimeters compared to 26 centimeters for 2040 sand under the same flow conditions. At 2 gallons per minute and 1 pound per gallon of 4060 sand, the equilibrium bed height is 29 centimeters of the total 30 centimeters. Now we're back to 12 gallons a minute, or 1/3 of a barrel per minute per foot of height. At 2 pounds per gallon 4060 sand, the equilibrium bed builds very rapidly and finally reaches a height of 27 of the 30 centimeters open in the slot. Thus, sand transport in thin fluids is characterized by a number of special features. 1. There will be an entrance length that is almost devoid of proppant. This is determined by the average velocity through the perforations. If one intends to pack the fracture at the end of the treatment, this is best accomplished by reducing rate, not increasing the sand concentration. 2. The equilibrium bed height will build at the angle of repose until it reaches the equilibrium height. Finally, that equilibrium height will typically be the majority of the created fracture height.